Hello and welcome to this lecture on fundamentals of electric drives. Now, in the previous lectures we discussed about converter fed DC drives. Today we will be discussing about chopper fed DC drives. When we have the DC source, we can have a DC to DC converter, which is also known as a DC chopper, to get a variable DC voltage out of a fixed DC voltage. And that variable DC voltage can be applied to the armature of a separately excited DC motor for speed and torque control. So, let us discuss about chopper fed DC drives. Now, we will be discussing first about the motoring operation and then about the braking operation. Let us take the motoring operation first. So, we will be discussing about motoring operation, and this is about a separately excited DC motor. Now, let us draw the circuit diagram of the chopper. So, we have the armature of the separately excited DC motor, and here we have a chopper switch. This is a transistor, a power transistor, and we have a freewheeling diode here, and here we have the DC source. So, the DC source is given as the voltage V, the chopper transistor is T, which can only conduct in one direction, that is from collector to emitter. This is the direction of current through the transistor when it is on, and the armature of the DC motor is represented by, as before, by this circuit. We have the armature resistance RA, armature inductance LA, and we have the back EMF, that is the E here. Now, the current through the armature here is IA, and the voltage that is appearing across the armature is VA. Now, let us see what are the various operating modes of the chopper. Now, when the transistor is on, we can say that when the transistor is on, so when this transistor is on, the current will flow from the source through the motor and back to the source in this following fashion. Now, which means the switch is on, we have the emitter and the base. So, we can apply the drive, the gate drive between the emitter and the base. So, this is the gate drive or the base drive here. The transistor turns on. So, the current flows from the source through the load back to the source here, and this is when this happens, what is the armature voltage? Armature voltage VA is equal to V, and that is equal to the resistance drop RAIA plus the inductance drop LA DIA by dt plus the back EMF, that is E, and this is called the powering interval. This interval is called the powering interval. Powering interval. and then after some time we switch off. This is the transistor T and we have the diode D, and when the transistor T is on, diode D is off. Diode D is usually off, is reverse biased. Now, when T is off, the transistor is off here. When we switch off the transistor, this current path is broken. So, there is no current here. So, we have the circuit in this case. However, there is no current flowing through the transistor. The current here will be freewheeling through the diode. So, what happens here is that this is off now. So, the current which was earlier flowing through the armature will be freewheeling through the diode. Now, this is when this is achieved, when under this operation the diode is on, diode D is on, and this is called the freewheeling interval. And when we have the freewheeling, what about the armature voltage? Because it is only freewheeling through the diode here, and the diode can be assumed to be an ideal one. So, in that case the diode drop is equal to 0. So, that is equal to 0. So, R A I A plus L A d I A by d t plus E. So, this is called the freewheeling interval. The armature current is freewheeling through the diode, because the armature has got sufficient inductance. If not, we can add some inductance in the armature circuit. The armature inductance has got some energy. This energy freewheels through the freewheeling diode, that is D. Now, if we draw the waveform of the voltage and current across the armature, we will obtain the following waveforms. This is the armature voltage, the x axis is the time axis here, and the current will increase like this and will decrease like this. In the steady state, the current will be exponential. It will be exponentially increasing and exponentially decreasing. So, in this case, this is the armature voltage V A, and this waveform is the armature current. Now, when the switch is on, the time here is T on. The switch remains on for the time which is T, and the time when the switch is off, that is called the T off. This is off time of the switch, and T on plus T off is a capital T, is the time period of the switch. So, this is how the chopper operates here, and we can define T on by capital T is the duty cycle. Now, what we are plotting here is the armature voltage and armature current. Now, in case of a DC machine, we are interested to draw the torque speed characteristic. So, we have to find out the average armature voltage and the average armature current. So, the average armature voltage can be found out by integrating the instantaneous voltage across the armature. So, we can find out the average armature voltage, that is V A, by integrating the instantaneous armature voltage, that is small v A, from 0 to T on, because the voltage is only finite from 0 to T on, and from T on to T off the voltage is 0. So, we do not have to integrate for that, and the time period is capital T, and V A for this is capital V, and this is T on by capital T, and we have already defined T on by capital T is delta, that is the duty cycle. So, we can say that V A is equal to delta into V, V is the source voltage. Now, this is the average armature voltage of a separately excited DC motor. Now, we would like to control the speed. Now, from this we can plot the torque speed characteristic. Now, if you use this equation and plot the torque speed characteristic or write the equation, our armature voltage is now delta V. So, this is K phi minus T R A by K phi whole square. So, this is the torque speed characteristic of a DC motor fed from a single quadrant chopper. Now, in this case, if you plot the speed versus torque, speed is in the y axis and torque is in the x axis. So, if we plot this, what we are varying here, to control the speed we have to vary the duty cycle, that is delta. So, in this case, if we go on plotting this, we say this is for one value of delta. So, delta decreases. So, we have another plot for reduced value of delta, further decreases and so on. So, this is for the increasing value of delta, delta increasing. So, when delta is increasing, we see that this is for delta 1, delta 2 and delta 3. So, delta 1 is less than delta 2 is less than delta 3 when the okay, delta is reducing here, delta is not increasing, delta is reducing here, delta is reducing, decreasing. So, when we write here delta, delta is maximum in this case, delta 2 and delta 3. So, delta 3 is less than delta 2. So, this is how we can write the inequality, delta 1 is greater than delta 2 is greater than delta 3. So, as it is reducing, we can see that this voltage will be reducing. So, delta V is armature voltage, and when delta reduces, V A is reducing, and when V A is reducing, the no load speed, which is the no load speed here, this is the no load speed. We can say that this is corresponding to omega m naught 1, the no load speed, omega m naught 2, omega m naught 3. The no load speed reduces here, and hence we get parallel lines in this case, and the decrease of delta, the no load speed also reduces. Now, this is for motoring operation, and this converter only operates in one quadrant, that is the first quadrant. So, this is quadrant 1 and this converter is operating in first quadrant only. So, this is called only one quadrant converter. So, here if you plot in terms of V A, so V A is positive here and I A is also positive. So, this only operates in first quadrant. So, if you plot here V A and I A, this converter operates only in the first quadrant. So, this is the quadrant number 1 here. So, this chopper or the DC to DC converter only operates in one quadrant, that is called quadrant number 1. Now, let us see the braking operation. Now, in case of braking operation, what happens here is the following, and we use here regenerative braking. So, we have a different circuit here. We have the armature, resistance, inductance and back EMF, and then we use the switch right after the armature. And here we have the diode. So, the position of the switch and the diode are interchanged, and the DC supply is present here V, and this is the transistor and this is the diode, maybe we can call T and D. So, this is the armature of the DC motor. So, we define the current in this direction I A. The armature voltage is defined like this as before. The current direction is reversed. If you see, in this case the current was into the armature for the motoring. In case of braking operation, current is out of the motor. So, we see that the direction of the current is changed here. So, this is how the chopper looks like. We have just the diode and the switches are interchanged. The switch is now in series with the voltage, and switch is now in parallel with the load, and the diode which was earlier in parallel is in series with the source like this. Now, let us say when the switch is on, we can say that T greater than 0 less or equal to T on. So, we turn on the switch. When we turn on the switch, what happens? When the switch is made on, this is on here, the back EMF is having a positive voltage. So, when the back EMF is having positive voltage, it basically circulates the current through the switch. So, this is called freewheeling interval, or this is called energy storage interval. The inductance of the armature is significant. So, we can add extra inductance. In this case, the energy is stored in the inductance of the armature circuit. So, the back EMF, which is the representation of mechanical energy, stores the energy in magnetic form in the armature inductance. So, this is called energy storage interval. So, this is called energy storage interval. And when it freewheels, what about the armature voltage? The armature voltage during the energy storage interval is 0. It means it is not connected to the supply. So, the armature is not connected with the supply, it is basically short circuited like this. So, the armature is shorted. So, when the armature is shorted, the energy, in this case the voltage is equal to 0. And then we turn off the switch. When we turn off the switch, what happens? T is greater than T on is less or equal to capital T. Now, this is called the duty interval. Duty interval. What happens when the switch is turned off? So, the current path is no longer present here. So, in this case the current path is broken. So, the switch is now off. When the switch is off, the current which was stored in the inductor, this inductive energy goes to the source. The diode turns on. So, it goes to the source. So, the source is getting charged, or the energy is fed back to the source, that is the duty interval. It means the energy from the armature circuit is fed back to the source. Now, here what about the armature voltage? Armature voltage here is equal to the source voltage, that is V. So, we define the duty cycle in a different way. Here the duty interval is T on to capital T. So, the duty cycle is, or the duty ratio here is T minus T on divided by capital T, that is the duty interval, which is from T on to capital T by capital T. Now, if we see the waveform here, the voltage and current waveforms, we can draw the voltage and current waveforms for the above circuit. Now, for the energy storage interval, the voltage is 0, that is from 0 to T on. So, when the switch is on, the energy stored in the inductor, the armature voltage is 0. So, what I am plotting here is armature voltage V A. So, in the y axis we are plotting the armature voltage and armature current. In the x axis we have the time. So, the current builds up here. The current builds up because the armature is short circuited earlier, and then at t equal to T on, the switch is off, the diode feeds the energy back to the source. So, the energy is fed back to the source. So, in that case the current decreases because V is usually greater than the armature back EMF. So, in that case the current decreases here because it has to flow against a voltage. So, this current is flowing against a voltage. So, the value of the current gradually reduces exponentially. So, this reduces like this. Again the cycle repeats. So, we have after T on, again this cycle repeats. It is a periodic waveform. So, we have the armature current which looks like this I A, and we have the armature voltage here. Now, in this case we can write down or find out the average armature voltage. So, the armature voltage here is basically rectangular voltage as before. It has got some 0 time or 0 interval, and we have plus V. So, this varying from plus V to 0. So, what about the average armature voltage? This is T off of the switch, and one cycle is the time period, that is the capital T. Now, in this case if you want to find out the average armature voltage, we have to integrate from T on to capital T. So, we have to integrate from T on to capital T, that is a duty interval, and for that time the armature voltage is V. So, this is what is average armature voltage. So, if we integrate this, we have the capital V being constant, it can be taken out of the integration sign. This is 1 upon T V integral T on to capital T dt. So, that is equal to V into T minus T on by capital T. Now, this is the expression for the armature voltage. Now, we know what is T minus T on by capital T, that is the duty ratio that we already defined in the previous discussion. So, this is the duty interval that we already defined. So, we can rewrite this as delta into V, that is all. So, this is the armature voltage which can be varied by controlling the duty cycle or duty ratio. Now, we can write down the full equation, that is equal to, if you see that E, if you see this particular circuit, the average voltage is the V A. So, we can write down this equation E minus I A R A is equal to V. So, E minus I A R A equal to V. So, let us find out the torque speed characteristic here. So, delta V or E is equal to delta V plus IARA, or we can say that omega m is equal to delta V by k phi plus IARA by k phi. The field is separately excited. Now, what about the torque here? The torque is given by this expression minus k phi Ia. Why we have a negative sign here? We have a negative sign here because we assume that the current is opposite of the natural convention. Usually current enters the armature, here we are assuming current is out of the armature. So, the torque here is negative. So, we have the expression for the torque, that is minus k phi Ia, or we can say that Ia is equal to T by k phi with a negative sign. So, we can substitute the value of Ia in this equation, and what we get here is delta V by k phi minus T R A by k phi square. Now, this gives the torque speed characteristic in this case. So, if we draw the torque speed characteristic of this motor, the speed is in the y axis and torque is in the x axis, but the torque is negative. So, since the torque is negative here, we are basically operating in the second quadrant, but this equation, if we plot this equation, we will get straight lines like this as before. So, these are for various values of delta, delta 1, delta 2 and delta 3, and decreasing, delta is decreasing. So, we can say that delta 1 is greater than delta 2 is greater than delta 3. But where are we operating here? We are operating in the second quadrant in this case, because the torque is negative. So, this is the first quadrant, we have the second quadrant here, and this is the quadrant for forward regenerative braking. So, equation remaining the same, we are actually operating in the second quadrant of speed torque characteristic. So, this is a way in which we can break the motor regeneratively. In this case, we are operating in the second quadrant of the torque speed characteristic. Here the torque is negative because the current is coming out of the armature, speed anyway is positive. So, we have to notice one thing, that here E is greater than delta V. So, by controlling the duty cycle, we are making the armature voltage less than the back EMF. So, the motor is usually operating as a generator. So, E is higher than delta V, and that is the reason the motor is operating under regenerative braking condition. So, we stop here for today's lecture. We will continue the chopper fed DC motor control in the next lecture.